All right. Well, good morning or afternoon, depending on when you're looking at this. I just wanted to do maybe a quick run through some of the Albert IO questions here, see if I could clear up any of the questions you guys might be having to help you kind of study for your test on Thursday. So for our first question here, Sepsi claims its soda stays carbonated longer than its main competitor, Poke. 8 sodas of each brand are randomly selected. They are opened, sealed back up, and then stored in a refrigerator. Starting on the third day after the sodas are opened, every 2 hours, the sodas are checked for carbonation. The table below shows the number of days the sodas stay carbonated. So we got one for Sepsi, one for Poke. Which of the following tests would be conducted to determine if Sepsi sodas do in fact stay carbonated longer than Poke? So this is the first clue right here that we need to look for in deciding which type of test we have. It's going to be one-sided because of this phrase. We're only looking for a greater than or a bigger than or a longer than. So all the two-sided ones are out. So we're not going to use the choice E or choice B. Those are gone. And then on this one, we just have to decide if we're doing a paired test or a two-sample test. And if it's two-sampled, if it's going to be T or Z. So with this one, I know the temptation is to pick A, the one-sided paired t-test, but there is no pairing that is going on here as far as looking at these things. So what I mean is, remember the whale watching one that we had? What we had, they were dependent on days. And so there was another row of things here that had list on here. We don't have that on this one. So the carbonation of Sepsi and the carbonation of Poke, these are independent of each other. There's no factor that's containing these together. These are two completely random samples. This one's random from this one. So a one-sided paired t-test would be out. So now we know it's going to be a two-sampled test, and we just have to decide if it's going to be T or Z. And so if I go through here and look, there's nothing in the problem that's telling me about a population standard deviation. So since we don't know what the population standard deviation is, that means Z is out. And so our final answer for this one is C. All right, for the next one, we're looking at the p-values for fantasy football. So fantasy football consists of a competition where participants select players from different football teams and points and are awarded based on the performance of those players. Students curious that the fantasy football totals for quarterbacks in the first 3 weeks of the season was a good indicator of how well players would do the rest of the season. The student randomly sampled 21 starting quarterbacks and measured their average fantasy football points for the first 3 weeks, and sampled another random sample of 21 quarterbacks and measured their average fantasy football points for the remainder of the season. The student then ran a two-sample t-test to determine if the number of fantasy football points in the first 3 weeks of the season differed, all right, from the fantasy football points of the rest of the year. So the data is shown below. The mean for the first 3 weeks is 2392 with a standard deviation of 1020. The mean for the remainder of the season was 1830 with a standard deviation of 920. After running a two-sided t-test, a p-value of 6.83 was calculated. How might you interpret the p-value for the context of the problem? Okay, so there's a lot of reading on here, and this is really the only thing you need, that you got a p-value of 6.83%. So that's the same as getting a p-value of 0.0683. Now, a couple things to keep in mind. This is a two-sided test. So this is the p-value after they multiplied something by 2. Then they got this p-value. So the regular p-value is probably less than that, probably something closer to 0.03, something, without using my calculator. And so not that we need that number for this one, but it does help us kind of understand what we're going through on this one. So 6.83% of quarterbacks have lower averages the rest of the season compared to the first 3. No, that's not what that number means. If there were really no difference in NFL quarterback performances during the first 3 weeks and their performance the rest of the season, getting differences in the sample means as large as 0.562 points or greater would be somewhat unlikely. In fact, about 6 points. So this almost sounds pretty good. Let me check the other choices, but I think B is going to be our solution here. And I'll explain why in just a second, as long as nothing else pops out. Approximately 6.83% of quarterbacks in the sample had higher average fantasy points. No, again, that number does not represent the amount of anything other than the p-value. It's just your likelihood of getting that sample. There's approximately 6.83 chance of this data occurring. again, that's close, but that's not quite exactly. It needs a little bit more, like if the null was true or something, or less. So if this was extreme, so we're gonna say no on that one. Approximately 6.83% chance of getting a difference of 50 points or less in the sample by chance alone. So this is, okay, so this would have to say or more, then we'd be good to go. And here's what I mean. So you have this graph here. You have this expected average, whatever it is. And if you get a t-score in this case that's equal to 0, then that means you're right here on this average line. So it didn't tell us what the t-score was, but the p-value is 6.83, meaning since they were checking for it being different, the combination of this shaded area and this shaded area gave us 0.683. So meaning the likelihood of getting this sample is out here in these outliers like this. So B is still looking pretty good, because if this one said or more, all right, the further difference of points we got, if this, as these points increase, say we got like 6 or 7 or 8 points, then what happens is we're moving further away from the average that we expected to get either way. And so based on our first 3 weeks, we expected to get a average of 2392, but the remaining part of the season, we only got 1830. So we separated between what we originally got and what we got a second time. There's a difference here, all right? And so the chance of getting this sample and this sample separated by this much was 0.063. So it's saying it's very rare, all right? And so your p-value would be indicating the likelihood of you getting that difference or more, not or less in this case, because you would be going further and further away from this one. So B is going to be our correct choice in this one, because getting differences in sample means as large as 5.62 or greater, which has what we're looking for, would be somewhat unlikely. And that's kind of what the whole point of the p-value is. As this number gets lower, right, as this p-value goes lower, we get less and less likely to get our differences or to get our symbol. And that's really the whole definition of a p-value. It's your chance of getting a weird, so to speak, outlierish number with the current information you have. And the smaller it is, the less likely that sample should exist if everything is true. All right, for the next one, we're looking at power, US versus China. We're not talking about military power, we're talking about statistical hypothesis test power. So a randomized experiment was performed to determine whether the average miles per gallon of cars manufactured in USA is different than the average miles per gallon of cars manufactured in China. Which of the following describes the power in the context of the situation? So again, when we're looking for power, all right, remember your little 2x2 table here, where your null hypothesis is true or your null hypothesis is false. And then you reject or fail to reject. And so power is this one over here. So when you reject a false hypothesis, that's a good thing, all right? Smiley face, happy. That tells you how good your test is doing. So you want high power. So we want to be able to reject a false hypothesis. So we have to figure out what is our hypothesis first. So in this particular case, we want to determine if the miles per gallon of cars manufactured in USA is different than those in China. So basically we have the average of America not equal to the average of, let's say, China. And so our null hypothesis is that they're equal, that there is no difference. So we want power to be able to identify this one correctly. So it is concluded that there is a difference. Okay, so that's good. In average miles per gallon of cars manufactured in USA compared to China, when actually the average for miles per gallon for cars manufactured in USA compared to China is the same. So that wouldn't work because that would be an error. All right, so if you make one decision, but it's really the other one, so we reject it when it's actually true. So that's going to be a type 1 error. So we don't want this one. It is correctly concluded that there is a difference. All right, so we're down here and that's actually what we want. So this is going to be the correct answer, but let's look at the other ones real quick. So on this one, again, it's correctly concluded there is a difference when there actually is. So that's power. We assume this one when we were able to decide this one when it's true. It's concluded the average miles per gallon of cars manufactured USA compared to China is not different. Okay, so that's not going to be power, so we don't want that one. It's correctly concluded the average miles per gallon of cars manufactured in USA compared to China is not different. So this would be a correct assessment, but it's not the power one. It's the one down here. So it's still correct. You fail to reject a true hypothesis. So there's nothing wrong with this one. It's good. All right, it's an okay decision. Just the problem is it's not power. And then E, it is concluded the average of miles per gallon of cars manufactured USA compared to China is the same when actually it's different. So this is the other one. This is going to be type 2 error. All right, so this one's beta and this one is alpha, but the one we want is B. So your answer for this one would be letter B. All right, for this problem, this one's obviously a more challenging one. It's a 2-sample mean interval and label difficult. So basically they give you this little chart here, and this is a donut coffee shop trying to figure out the 95% confidence interval for the difference in the average number of cups of coffee per day between adults and teenagers. You don't actually have to find the answer, which would be easier. You have to figure out which one of these would be the correct formula. Now, for our class, we're not actually using the formulas all the way, but there's a couple of them that we can look at here that we can eliminate easy because they have missing parts. So this one and this one we'd take out because they're missing the sample size. So it's definitely not going to be B, and it's definitely not going to be D. And then it's also not going to be E as well because it's missing the either T or Z score. So now you know you only got 2 choices, A and C, and basically you just have to figure out, is this the correct number or is this the correct number? So this, if you memorized it, is the Z score at 95%. Now, as you're looking at this particular problem, you can see that we don't have the population standard deviation. What we have is the standard deviation for the samples. So this is the standard deviation of X. So technically we shouldn't be doing the Z-score one here. So we know the answer is going to be C just from process elimination. But the question is, how do they get the 1.982? So the easiest way I found to do this using our calculator is to go to the stat function, then go over to the tests, and then look at the 2-sample T interval, which is option number 0. When you click on that, make sure you're highlighted on stats because you're going to enter in a few things. And so you have a label that says like X1, sample X1, and then N1, and then underneath that you have sample X2, standard deviation for X number 2, and N for X or N for number 2. And all these numbers are the ones in the chart. So it's 1.8 and 0.6 and 75, and it's 1.3 and 0.3 and 75. And so you plug all those in, make sure you put the C level at 0.95. And then make sure you say no to pooling. We don't pool. And then we go all the way down to the bottom, we hit calculate, and then we need one number from the screen here. You're gonna see that it says DF is equal to 108.82, and that keeps going. So normally our degrees of freedom are always going to be whole numbers, but if we keep this number real quick, and we go to now option number 4 in the second vars category, so this is under second vars, we're going to see that we get the inverse T function. It's going to ask us for area. It's going to ask us for degrees of freedom. Well, we know our area for this one's going to be 0.975, because remember at 95%, you add in the extra bit to the left there, and then go ahead and substitute this number in for degrees of freedom. So 0.975 and then 108.82. If I press enter, I will see that the answer will be this 1.982 sitting right here at the, so this is the T score, 1.982. This is definitely the more advanced way to guarantee to find this number if you're looking at where'd that number come from. But again, if you're using process of elimination, if you've been kind of paying attention at all during class, you know these three were out because they're missing things. Okay, so don't even fall for B, D, or E. And then A and C become your comparison. And hopefully by now you guys are kind of familiar that 95% and 1.96 is the Z-score. And because we don't know the population standard deviation, we limited it out. So without having to do any of this, this is all just extra if you want to prove that number is correct. But without doing any of that, just by process of elimination, I know that the answer is C. All right, for this one's labeled as a pretty easy problem. And what you're doing is looking for which one of these would be appropriate for a 2 sample or a 2 proportion interval. So remember, proportions deal with percentages, typically need to be yes or no, this or that. They're very categorical. There's not a lot of numbers here. So anything that would have an average or anything that deals with one individual is not going to be counted. So comparing whether men earn more money than women. So this is a numerical thing. We'd find an average for, that one's out. Determining the proportion. All right, so we got percentages. That's good. Of people who attend church at least 1 a week. Problem with this one, this is only a 1 sample thing. You don't have people broken into 2 different groups. So why it looks nice, it doesn't work. Comparing whether dogs are more likely to live longer than cats. Again, we're going to have numbers here, averages, not percentages. Determining whether males or females are more likely to exercise regularly. All right, we do have 2 different groups here, and we could ask a yes or no question on this one. So this is a good candidate. Examining whether a relationship exists between grade point average and hour study. This is not even a hypothesis test. This is linear regression. So that one won't work. So just by a process of elimination, D ends up being the best one. Because these 2 are averages. This is 1 sample and this one's regression. And the reason why this one works as well too is because it's a yes or no question determining whether males or females are more likely to exercise. So you could find a percentage of males that say yes, they're going to exercise, and compare that to percentage of females that say they're going to exercise by asking them a yes or no question, and you're good to go. These are actual measurements, so they're going to be a little bit harder to do percentages on. Because you're not going to say like, this percent of dogs is more likely to live than this percent of cats. That would be kind of weird. You would compare their actual ages. Again, this is 1 sample, so that's not even in the consideration. And then money is also an average thing. So there you go. All right, for this one, we're doing a t-test, not t-test, a 2 sample hypothesis test with proportions. Because you're looking at a Z-score and percentages. So let's go ahead and kind of read through this to see what we got. So once upon a time, a greater proportion of males played video games than females. So this automatically tells me we're dealing with percentages. They're saying the proportion of men who play video games than females is higher. We got Katana, Jade, Laura, and other female gamers wanting to know if this is still true and decided to investigate. Assuming all conditions were satisfied, so that means all the assumptions were met, a Z statistic of Z equals 1.08 was obtained from a test using the following hypothesis. So this one is their null, this one's their alternative. They ran it in the formula for Z and they got 1.08. So normally what we do from here is we plug this into the calculator and determine a p-value, because remember, you can't make a decision without your p-value. So since this is a Z-score, you want to do option number 2, which is your normal CDF function. And then it's going to ask you for a lower, an upper, and let's see what else it does. Option number 2, second vars, lower, upper, average, and standard deviation. So we'll leave the average and the standard deviation at 0 and 1. We're not going to change those. And so what we have to do is figure out, does this 1.08 go on the upper or lower one? So if we revisit our famous bell curve, again, remembering that a Z-score of 0 means you're right at the average in the middle. Positive numbers are going to be over here on the right. Negative numbers are going to be on the left. So 1.08 is going to be somewhere over here. And we're testing in this area. And so this becomes my lower limit. And this becomes my upper limit, the infinity. Because technically my shading is going in this direction to infinity. So if I type into my lower limit 1.08 and my upper limit 1E99, I get a p-value of, and this kind of goes back to unit 1, unit 6, 0.1401. All right, so that's our p-value, and we're going to compare it to alpha of 0.05. That's our default setting. There's nothing in there saying anything else. So our p-value is greater than alpha. So basically, we do not have enough information. We are going to reject the null. So we need to look for an answer that says something like that. So what should our friends conclude based on that? That the original assumption they still go with. So it's still, they should assume that it's still equal. So since the sample of females produced a greater proportion of gamers than the sample of males, it appears that the proportion of females for video games is now higher. No, it's not higher. Since the sample of males produced a greater proportion of gamers than the sample of females, it appears that the portion of males who play video games is still higher. No, again, it's not higher. We're going with this one because our p-value said to reject, or failed to reject, sorry. Failed to reject HO, so our p-value was higher. So yeah, that's supposed to say fail, I apologize. C says the p-value of the test was greater than 0.05. It was. We do not have enough evidence to rule out the possibility that the proportion of females who play video games is now equal to the proportion of males. Okay, so that one looks good. Let's check the other two to make sure. Again, we said these two are out. Says the p-value of the test was less than. No, it was not. So we cross off this one. Since the Z statistic is greater than 1, yeah, it is, okay. The observed difference in proportions is more than 1 standard deviation above the mean difference of 0 because this happens so rarely. It happens this often, which is not rare enough. So it's already getting a little fishy. We're gonna cross that one out. So C is gonna be our correct choice. Again, just kind of based on the other one's not really being that good. We're going with it, it's equal. We're failing to reject because p-value is greater than alpha. This was kind of going in the right direction. E would have been a maybe choice until it started saying so rarely. In statistics, we'd count rarely to be whatever less than our alpha is. So there you go for that one. All right, for the next one, convertibles, conclusions from a confidence interval. This whole thing basically goes through to say that a 90% confidence interval with negative 0.021 and 0.115 for percentages of men and women. So they're basically trying to find out a sample of women who had recently purchased a new vehicle and then determine both the proportion of men and the proportion of women who had purchased a convertible. Based on this confidence interval, should the marketing firm conclude that the proportion of men who purchase a convertible is higher than the proportion of women? So it's tempting, right? Because this number here is bigger, but in fact, the only answer you can go with is no. And he will explain why. So that's going to eliminate this one, and this one. And the reason why we got to say no, we cannot conclude that the men is higher than the women is because 0 is in the middle of this. So since 0 is included in the confidence interval, there may be no difference, and that's the one we want. So D ends up being the correct answer. It doesn't have anything to do with the ends. It has everything to do with the fact that 0 is in the middle. So this whole interval would have to be either above 0 or it would have to be completely below 0 to say for sure one is higher than the other. But the fact that 0 is in the middle means that there may actually be no difference between the two. So remember, the whole point of this unit is to look for if there's any difference between the two things. All right, for this one, this is another one of those, you get one type of test and you got to look at the other end. So 2 samples Z test for proportions had these hypotheses that the difference between 1 and 2 is non-existent, and there is some difference between 1 and 2. So this is a two-tailed hypothesis test. It resulted in a p-value of 0.04. So that means if we want our interval to contain 0, we would want to fail to reject. And in order to fail to reject, your p-value has to be greater than your alpha. So if we do a 90% confidence interval and we have a two-tailed test, then our alpha is going to be 0.1. And 0.04 is actually less than 0.01. So with number 1, we would reject the null hypothesis. Therefore, number 1 is out. With number 2, at a 95% confidence interval, we would have alpha then equal to 0.05 for a two-tailed test, and therefore 0.04 would still be less than alpha, and again we would still reject HO. So again, don't want to do that one. So our only one is going to be number 3, because at a 99% confidence interval, our alpha is going to be 0.01. In this case, our p-value of 0.04 is going to be greater than that, so we're going to fail to reject here, meaning we're going to continue to go with this one, which contains 0, and that's what we want down here. And so our correct answer is B. Number 3 is the only correct answer for this one. All right, for this particular problem, again, you're trying to pick the formula. I know we don't use this much in class, but you're trying to pick out the correct formula that matches the scenario up here. So you've got 2 samples of 200, one from Canada and one from the US, it looks like. And let's see, 136 people in the US and 108 people in Canada. So you have 2 different proportions going on here percentage-wise. If you want to figure them out, you can. That'll help you out with the numbers on top here. But you really don't need to. Basically, the big key here is to figure out the z-score at 98% in the calculator. So again, this is option number 3, the inverse norm inside the second var stuff. And then use 0.98 for your area if you do the center, or use 0.99 if you do it to the left. But basically, you'll find that the z-score for this 98% is 2.33 when rounded. I got 2.3263, so they rounded to 2.33. So this helps me eliminate 2 problems right off the bat because the z-scores here are wrong. So those are probably the t-scores. The other thing is the first one, we don't, when we're doing 2 samples, we're not going to have just one set of percentages on the top. So A is out, and basically you just have to figure out between B and C, both of which have this, and this correctly is the correct one. So you got to carefully look inside the formula. And right away, I see a problem right here with these 2. So the details are not always obvious, but they are right there in front of you. This has the same percents for both fractions, 0.61, 0.39, 0.69, 0.39. They're not the same. So that means B wasn't written correctly. So again, by process of elimination, as you're going through these, C is the correct choice. So if you guys click on the solution thing, it talks about how you could work all these problems out and see which one gives you the intervals, yada, yada, yada. That's going to take forever. Look instead for the key things that are going to be different. So we know how to find a z-score. Mr. G, how do we know this is z-score? Because again, we're doing percentages, proportions right there. So you can only do z with that one. So that was just a quick little inverse norm at 98% in the center. I found 2.33 to be my z-score. So that only left the top 3, the bottom 2 are out. And then, like I say, look inside the square root. You need to have 2 samples, not 1. So A is out. And that left it between B and C. And these were the same percentages, 0.61, 0.39, 0.61, 0.39. No, these are 2 completely different percentages. So C was my only choice. All right, for this one, this is, again, another one of those. You have a hypothesis test. It gives you a p-value. Which confidence interval would you use to make sure, you contain 0? So this one is just like we had before. Our null hypothesis is that there is no difference, and our alternative is that P2 is larger. P1 minus P2 gives me negative numbers. So the test produces a p-value of 0.043. So we want to fail to reject. So we want our alpha to be smaller than this number. So since we're doing a one-tailed test at 90%, our alpha there, all right, so for this one here, alpha would have been equal to 0.05. So again, remember how I get alpha from my confidence intervals. If I have a 90% confidence interval, that leaves me 10% of the area left over for my hypothesis test, but we're doing a one-tailed, so we divide the 10% by 2, and we get 0.05. So at 90%, we would reject the null and accept this one. We don't want to do that. At 95%, my alpha is going to be at 0.025, because I have 5% left over, and I divide that by 2. So this one will work. This one we will fail to reject, and therefore 0 would be in my interval. So if it works at 95, it's going to work at 99, because alpha here is going to be at let's see, we got 1% over, so 1% would be here, 0. So it's like that, 0.005. But again, both of these all right, are going to cause the p-value to be greater than alpha. And anytime p-value is greater than alpha, then you go with your null hypothesis, which is what we want because it's got 0, which means those go here. So 2 and 3 work, which means D is our final answer on that. So this one, again, very similar to the other one. Let me know when you guys have questions on this when you get to class. All right, for this one, we're looking for which one of these would be an actual matched pairs experiment. So whenever you're doing a matched pair, the thing you need to remember is you're really looking at one sample with a matched pair, even though you're looking at 2 samples, yes, but your one sample is all you're testing, it's the difference. All right, and so when you set up a matched pair, you usually have like something that relates the other 2 rows together, you subtract them, and then whatever those differences are, that's kind of what you're doing. So that's automatically going to eliminate this one, because these are comparing 2 completely independent samples. And with a matched pairs, we want one sample that's kind of dependent. All right, so if you go back and look at the notes, that's what we spent time saying, like dependent on everything. So those are out. And then whenever you're comparing differences between something, 0 is going to be a part of the equation. So because there's a possibility there is no difference. And so this right here is out because this has 5.1 as your null hypothesis. So now we just got to figure out what the appropriate null and alternative would be. And so he wants to determine how long individuals can hold their hands in ice water when intoxicated compared to sober. He hypothesizes that the alcohol will numb the pain, so individuals will be able to keep their hands in the ice water longer than intoxicated. So his alternative is going to be testing if the average is indeed longer than something. And so that leaves me with C as my choice for this one instead of E, because E would be for less than and C would be for greater than in this particular situation. All right, for this one, we are running a hypothesis test again, a 2-sample t-test, and a confidence interval for the heck of it, to be exact. Basically, an office manager wonders if free bagels are going to make people work more. She gives 35 workers randomly bagels and another random 35 workers not bagels. Data's here. The difference is U1 minus U2, so she wanted to know the difference between these. 95% confidence interval states that negative 0.538 and 1.698 could be the difference 95% of the time. She actually ran a t-test of the difference and got a t-value of 1.04, which then translated to a p-value of 0.304 with degrees of freedom of 67. So what practical conclusion can be made off of this data? So here, let's look. Oh, let me clear my writing there, sorry. So letter A, there is a strong evidence that bagels do not cause workers to put in more hours. All right, so we got to be careful with the phrasing the word, there's strong evidence. That's true. We do not see workers putting in more hours because of the bagels, and I'll explain that in a second. So this one's a maybe. We'll come back and revisit this one. There is strong evidence that bagels do cause workers to put in more hours. And the answer for this one is no, there is not. And here's why. Your p-value is greater than whatever alpha would be. So in this case, we would say there is not enough evidence. So not enough. Also, if you look at your confidence interval, somewhere inside that confidence interval is a 0. Both of these things mean that no, there's no evidence that there's any difference between those who got the bagels and didn't. The evidence is inconclusive, so no conclusions whatsoever can be drawn. No, not necessarily. That's just a lazy way of saying like I didn't find anything. We did find that we did find enough evidence to suggest there's no difference. I guess if you want to look at it that way. A moderate correlation appears between bagels and workers' hours. No, we didn't even do regression analysis. Based off this experiment, there is insufficient evidence that the bagels cause an increase in worker hours. So this is the right answer because the phrasing is better. The phrasing, there is insufficient evidence, comes directly from our notes and from our textbook and from everything else we've been doing. Whenever, again, the p-value is larger than alpha, that's your phrase. That's what that means, that your sample size can be attributed to random chance. So that means not enough evidence that bagels cause an increase in worker hours. So that's why the strong evidence part here, the conclusion here was good, but the fact that there's strong evidence for it, no, it's just random chance. So that makes E the better choice. All right, for our next one, we're looking for an error, type 1 error to be specific. So the CCO of a local fast food chain is considering two different advertising campaigns. One campaign focuses on low prices, while the other campaign focuses on great service. In the same large city, 15 randomly selected stores within the chain focused on low prices, and another 15 randomly selected stores within the chain focused on great service. The CEO hopes to determine if any significant difference exists between the effect of the two advertising campaigns, describe a type 1 error in the context, and give the consequences. So in order to know what our type 1 error is, we got to kind of know what our hypothesis is. For this percentage, or this one, let's see, let's just say that the average of 1 and the average of 2 are equal, that there is no difference. That's going to always be our assumption until we're proven otherwise. So that means in this case, the two of them are actually different because they're looking for significant difference. So there is a difference. So a type 1 error, again, going back to my chart, is going to be up here at the top. So type 1 is alpha up here. Type 2 is beta here. This is our power. And this is just correct. All right, so again, this is when the HO is true. This is when the HO is false. This is when you reject. And this is when you fail to reject. So if you reject a true hypothesis, okay, if you reject this, you've committed a type 1 error. So we need to find that from down here. So incorrectly identifying the campaign that focuses on low prices as better when it is not. So incorrectly identifying the campaign that focuses on low prices is better. So basically deciding there is a difference when there is not a difference. Consequence of coordinating a failed campaign. So incorrectly identifying the campaign that focuses on low prices as it better. Okay, so this is a maybe. I gotta go back and read that one again. Not saying that one's right, but it's a maybe. Let's see. Incorrectly stating that the low prices fails to increase sales. Consequence, incorrectly stating that the low prices campaign. Okay, so the wording on this is what makes this difficult. Incorrectly stating that the low prices campaign fails to increase sales. Incorrectly stating that the low prices campaign fails. So incorrectly saying that this is true. So incorrectly saying that this is true. So failing to reject a false. So that would be a type 2 error. That's beta. So we don't want that one. Incorrectly identifying the good service campaign is better when it is really not. Oh, okay. I get what I'm doing here. Okay. So the problem with these first ones, okay, now I know I don't like A because it's just saying better. What kind of test do we have? We got a two-tailed test. So Mr. G, stay focused on the mission there. So two-tailed test is we're looking for differences. So type A is just looking for better, don't care. This one's just looking for one's better, don't care. Incorrectly identifying the good service as better. Again, this is just looking for better. We're looking for just stating that it's different. So until we even find the right phrasing, we're not even the right thing. Failing to determine it. Okay, so here we go. This one says something about a difference. Determinators. Okay, so these two are the only two to look at. So all three of these are out because they're only looking for this stuff. Okay, and we're not looking for that. So that's why A, B, and C are out. So now let's look at D and E. So wasting my time reading the thing. So failing to determine a difference in sales that really existed. So that would be failing to identify this. So that would be a beta error. So that means E has to be our choice. So determining there is a difference. Okay, so determining that you want to go with this when there is no difference. Perfect. That's exactly what we want. So you've made the decision to reject when you shouldn't have. The company would incorporate a campaign, but would not be overly successful increasing sales with it. Yes, very good. So E is going to be our choice. Okay, so let's sum this back up with all this weird, confusing language. So again, the first three were out because they only looked at something being better or worse. That wasn't what our question was. Our question was looking for something being different. So they were gone just based on that phrasing, leaving us with D and E. This one's type 2 beta. We went with this one when we shouldn't have. And then type 1 is alpha. We went with this one when we shouldn't have. So E would be your choice on that one. So the wording on these is a little difficult. Just be careful when you guys read these. Don't get confused like I did looking at the better or not better. All right, for this one, we're trying to determine what gives us the greatest power. Remember, power is your ability to properly reject a hypothesis that is wrong. That's the whole point of power. And so in a hypothesis test, the HO, the percentage is equal to 0.8 versus the percentage being greater than 0.8 of the test would be the greatest for which of the following choices. So basically, which one of these is going to increase power? And there's two ways to increase power. Hopefully you guys remember two main ways. And we talked about this over the notes and you guys said it in class. Number one, easiest way is always to increase the sample size in. So this one here and this one here would be the best of that because n is 240. So let's cross those out. Option number two that will work for you is to increase alpha. And so the larger you make alpha, the greater your power. Now, this one does come at risk of type 1 error increase, but that's okay. That's not what this problem is asking for. So that leaves this one out because they both have the same sample size, but this one has an alpha of 0.1. So yes, it can be determined from the information given. This one's actually fairly straightforward. It is answer D. It's just basically making sure you understand the two ways that you can increase your power, and that's by increasing your sample size, and increasing your alpha. All right, for this one, it's basically asking you why a confidence interval would be better than a hypothesis test. So it goes through this whole thing and basically says a psychologist is basically measuring heart rate, has patients walk for 5 and then run for 5, Here's all the information. So why would a confidence interval be more useful in this situation than the hypothesis test? And so as we read through these, we can kind of address these as we go one by one. A confidence interval meets the conditions necessary while hypothesis test does not. No, the hypothesis test works just fine. They were able to do both of them. We're good here. A confidence interval have more power than a hypothesis test? Nope. Confidence intervals do not have power, so that one wouldn't be true. A confidence interval will have a lower margin of error than a hypothesis test might. No, that's not going to be anything to do with the difference. They're all going to have the same deal there. A confidence interval gives more detailed information than a hypothesis test does. Maybe, we'll come back and see. There is a lower chance of a type 2 error in a confidence interval than in a hypothesis. There's no type 2 errors on this one, so just by process of elimination from the other less than ideal choices, D is right. And let's kind of look at D and see why this might make sense. A confidence interval gives more detailed information than a hypothesis test. So here's our confidence interval here and our hypothesis tests. Let's see. They didn't plug it in, but if you did a hypothesis test, you can basically only get one of two things from a hypothesis test. Either that your original hypothesis is good or that your alternative is good. It's not really going to give you the details on what the actual difference is like a confidence interval will. So if the psychologist is interested in explaining to his or her patients what, how much more beats per minute or heart rates or whatever they can expect after running, then the confidence interval gives them a better idea of the actual numerical difference between the two samples. Whereas a hypothesis test would merely test a sample against it to see if it makes sense or not. So D is a good answer, but this is kind of a weirdly worded question. So in most cases, a confidence interval is a little bit more informal or informational, I should say. All right, well, this one's just basically the opposite of what we just did. Who has the smallest power? So earlier we were looking for the largest one. Now we're looking for the settings that are going to give us the smaller power. So we do have enough information just like before. And again, as a reminder, the two ways to increase power are to increase sample size. So we're going to want to do the opposite. We're going to want to make it smaller, and to increase alpha. So in this case, we're also going to want to make it smaller. So this would help us lower or decrease power if we did what the arrows say. So we would want to bring our sample size down and bring our alpha down. So that eliminates these two. They have higher sample sizes. And then this one has the lowest alpha. So A would be our correct choice. The smallest sample size and the smallest alpha will give us the smallest amount of power. I'm not sure why you'd want to do that, but that is the way to go on that one. All right, for this one, we're looking at ways to decrease a type 1 error. So we want to make type 1 small as possible. The easiest way to do that is to decrease alpha. That would be the easiest way to do it. But we'll look and see kind of like what else is going to happen when we try to make type 1 small. So again, the easiest way to do this is to decrease your alpha. So make alpha go to like 0.01, 02 instead of 0.05. So this is asking if she does that, if her level of Allison does adjust her significance test so that the possibility of type 1 errors reduced. So that's what she did. She decreased her alpha. She made it smaller. Which of the following will also happen? So the significance level of the test will be increased. Well, no, she just decreased it. So 1 is out. The probability of making a type 2 error will increase. That is true. So as your alpha gets smaller, the space that your alpha leaves is taken up by your beta error. So yes, number 2 is a correct statement. The power of the test will decrease. Yes, power is based on your alpha size and your sample. So she's using the same sample size, which I assume she is, but decreasing your alpha, then the power of the test will also be decreased. So we're looking for the one that says 2 and 3 only. E is our answer. So again, anything with 1 in it is automatically out because that's opposite of what she said she was doing. And it's not just 2 or just 3, it is both of them. All right, for this one, we need to determine which hypothesis is correct for our heights of twins, twins being the key here. Random sample on heights of 50 pairs. Let me just go ahead and just write that out real quick before we get too far along. This is a matched pairs test. So a random sample on the heights of 50 pairs of 18-year-old identical twins, all right, were matched up based on the fact that they're identical, was used to determine whether the second born twin tends to be taller than the firstborn. Interesting. Let the second average represent the average height of the second born, let the first average represent the firstborn, and let the UD represent the difference between the height. So the height of the second born minus firstborn for all pairs of twins. Which of the following would be null and alternative? So this has matched pairs stuff written all over it. So if you're confused by these terms, and this is what I would study, the matched pairs stuff. Like everything in here is what we went over the notes the other day. So with matched pairs, you need a UD in it. So this is going to be out, this is going to be out, and this is going to be out because these are all dealing with independent samples, and we don't want that. We want to deal with dependent samples. They're dependent on the fact that they were born together. So basically, which of the following would show that the height of the second born minus the height of the firstborn? So we would want to see positive numbers, because they're taking the second one minus the first one. All right, so the average of the second one minus the average of the first one to get their difference. And if the second one is indeed taller than the firstborn one, then these would all be bigger numbers being subtracted by smaller numbers, therefore giving us positive numbers. And so this would be our answer here, because this is where we're going to be testing that the differences are greater than 0, not less than 0. So that's really the only hard part, is just making sure you're going in the correct direction on that one. All right, earlier we were looking at reducing type 1 errors. Now we're looking at reducing type 2 errors. Ways to reduce type 2 errors are, again, you can always increase alpha. As your alpha gets bigger, your type 2 is going to get smaller. So that's one thing we want to look for. And always, anytime you want to reduce your type 2 errors, that means you're increasing power. So remember, power is 1 minus your beta, which is your type 2 error. So as this goes down, your power goes up. So how do you increase power? You can also increase the sample size. So things you would do to increase power are going to be things you do to decrease beta. So that's increase alpha, increase sample size. So boom, boom, and then use matched pairs experimental design. No, we never talked about that. So you're looking for the one that says answers 1 and 2 only. Letter D is your choice. So just make sure you go back and again, look at those multiple choice questions that we had on the quiz. We'll go over those in class, but that's where you guys kind of will be looking at. All right, so again, we've got another one of these where we're trying to figure out what the heck the p-value actually stands for. So he runs this dean at a university runs a hypothesis test where the assumption is that the percentage of students who experience heart palpitations is 0.18. And the alternative is that the, let's see, the Dean random sample of students from the University of just interviewed found that 6% experience for p-value reports test. Which of the following statements is best interpretation p-value? So it looks like is less than I got answer. I was looking for 0.18. Okay, so there's his original assumption. So basically he gets his p-value of 0.3. Which we know at 0.3, since it is greater than typically every alpha we use, we would fail to reject, meaning we would still go with this one right here. So as we're going through it, why did we decide to do that? So the probability that the alternative hypothesis is true is 30%. No, that's not what the p-value stands for. It's not a probability that the alternative is true. It is a different probability, and I bet you'll say it on here. The probability that the null hypothesis is true. Again, no, it is not probability that one of these is true. The proportion of students who experience heart palpitations at the university is 18. Then the probability of observing results of at most 16 is 30. Ooh, that one looks really good. And I'll explain that one in a second if that's the best one. Let's see, proportion of students 15. Oh, no, we don't want at least, we want at most. So yep. Probability of observing 16% of students who experience heart palpitations at the university is that no. All right, so here's why C is good. So again, go back to our graph here. And we've got whatever our t-score was, yada, yada, yada. Since we're doing a less than, we shaded this side. So basically this shaded area is equal to 30%. So again, remember the chance of you getting a number that is at this or lower is 30% if this original average of 0.18 is true. And that's what then the probability of observing at most 0.16. So that's what that means, at most. So your p-value is saying that if your null hypothesis is true, the chance of the sample you got existing by randomization alone is 30%. That's what the p-value is. And it's always at that or lower in this particular case. So letter C would be your best choice there. All right, type 2 error time. So what is a type 2 error? In this situation, this little girl is hoping to not go to school tomorrow and sees that the forecast is calling for 6 inches of snow overnight. Based upon past history, she knows that school will be canceled if more than 3 inches of snowfall. Therefore, she forms the null hypothesis that there will be no school tomorrow. So the HO is no school. And the alternative is school as usual. All right, in this situation, what would be the meaning and potential consequence and of making a type 2 error? So type 2 error is down here at the bottom. That's our beta. That's when our null hypothesis is false and you fail to reject it. So you should have thrown it out, but you didn't. And so she made the assumption that there would be no school when the alternative is there is. So she assumed this when in reality it was this one. So here's her type 2 error. So Anna decides that the weather report is wrong. As a result, she stays up late in order to complete her homework and study for the test that she's been scheduled tomorrow. Oops, oh well, it snowed and the school got canceled. Now, school didn't get canceled in this scenario because the HO was false, so A is out. Anya decides that the weather report is wrong again. As a result, she stays up late in order to complete her homework, study for the tests. It turns out that she was right. It barely snowed when so school is not canceled. All right, so school is not canceled, but she was not right, so B is out. She truly believes that tomorrow will be a snow day and she will get to sleep as late as she wants to in the morning. As a result, she decided not to do her homework or study for the test. Thank goodness she was right. No, she was not right. Obviously, she's making an error. That's the whole point of this one. She truly believes tomorrow will be a snow day. All right, so she believes this. That's her decision, and she will get to sleep as late as she wants in the morning. As a result, she decides not to do her homework. Study for the test. Oops, it doesn't snow at all, and school goes on. She can only hope that her teachers do not check homework and that she passes this test. After all, she's really tired from late night Netflix binge. That's probably gonna be her choice. Let's look at lesson. Anna is making mistakes all over the place. She makes mistakes in her homework. No, that's not what it. Okay, so D is the correct choice. So what happens in D is she assumes this is the case, right? She fails to reject her null hypothesis, but it turns out to be false. This one is actually the right answer. And so that's what type D is saying. All right, last one to look at, again, looking at errors. So hopefully you guys are studying these things because they keep popping up. So making a type 1 error means that you reject a true null hypothesis. So this is the actual answer. And this is what you decided. So we're going to go through here and look and see. The rest of this is just the whole, you can read through it if you want, but it's actually the same thing. So this is the true one. This is what you decided. So in this situation, what would be the meaning and potential consequences of the physician making a type 1 error? The physician believes that the patient has diabetes. No, because you decided that they do not. So that one's already up. The physician decides that the patient does not have diabetes, okay, and therefore does not treat the patient for disease. However, the physician was wrong. The patient really does have diabetes and is not receiving treatment that is necessary. This could be very dangerous. That seems like the right answer, but let's check the other ones. The physician made a mistake when testing the patient's blood sugar readings. Okay, no. The physician determines that the patient does have diabetes. No. The physician determines the patient does not have diabetes, okay, and therefore does not treat the, it turns out that the patient really is not diabetic and simply had no. Okay, so that would be the person's right. All right, so B is the correct answer again, because they made the decision that the patient did not have diabetes when in fact they did. And the consequence is, again, they're not getting treatment. So this sums up these Albert IOs. I don't know if this helps or not, so you guys kind of let me know as you're watching through it. All of these things can be solved based on the stuff we've talked about in class and the notes, so don't get overwhelmed by them, but do know that your multiple choice questions are similar to this type of stuff. So going through these and actually practicing will make a difference. All right, guys, have a good day.